Welcome to video 7.4 about power. Now, power is a new concept. It's one we're going to see briefly here. It'll pop up again once or twice in the rest of semester one, but it will become even more important, more central next semester. Power is in physics land has to do with the rate that work is done. We've been talking about work being done. Okay. A force acting through a distance. Me pushing my sofa down the hall, for example. If I push it faster, it turns out I expend more power. Think of it this way. How do I have it worded here? Power, given by the symbol P, believe it or not, is a measures do I have it written here as the rate? Measures, let's do it this way. Let's be a little bit more colloquial here. Measures how quickly my pink pen is dying. Let me see if I can grab this old pink pen. How quickly, wow, look at that. Work is done. Power P measures how quickly work is done. Well, that sure is a loud marker. Power P measures how quickly work is done. It's a rate. So, that's my first bullet point. Second one is, I'll write in green now because of those weird pink markers. If work W done by whatever force, either it's the net work or it's the work done by a particular, doesn't make any difference. If any work W is done in time t, comma, then power is defined as work W over time t. That is how we define power. Work done divided by the time required to do that work, whatever that work may happen to be. A couple comments here. Number one, units. Let's look at the units for a second. Well, obviously, work, like energy, is in joules. T is in seconds, so units are joules per second. Okay. But there's a name for that unit. You know how newtons is what we call a compound unit? It's made up of kilograms, meters, and seconds in a certain combination to get a single newton. Well, a joule is the same thing, but then we further put joules and seconds together to make a new unit. 1 joule per second is equal to 1 watt. That's right. Our old familiar watts that come from light bulbs. That's one of the few places I can think of in our everyday life that the metric system makes it into everyday life. The watt for power. The symbol for watt is capital W. All right. There's another sort of familiar unit of power, and that is the horsepower. 1 horsepower. So a horsepower is a unit equals 1 symbol is HP. That's what, 746 watts. Okay? And that's a more familiar unit for things like we talk about the horsepower of an engine or something like that. But it's a unit of power. It tells you how quickly work is done. Okay? To get a sense of what a horsepower is, if average weight person, say 120-pound person, sort of walks up steps at a leisurely pace, just a modest, normal, everyday pace. That person is doing work at a rate of about 0.2 horsepower, or about 150 watts. Okay. So that's to give you a sense. Okay. Walking up steps at a leisurely pace is about like I said, about 0.2 horsepower, or about 150 watts. All right, so that is how we define power. Now for a very quick example of a calculation of power. Say you're in a car. Here's the, nope, I want a blue street. Here's the street. You're in a car, and you need to pass a truck. Let's make a big green truck, your big green box truck here. Okay, how's that? Lovely. And your initial velocity is, let me see the numbers here, 13.4 meters per second. That's your initial velocity. And you need to pass this truck, and yeah, there's an oncoming car, and you need to get around this truck in about 3 seconds. Okay. And that's going to require your final velocity. So you're going to pass the truck, basically. You're going to get across the dashed line and pass the truck, and your final velocity is going to be higher. You will have sped up, accelerated to pass the truck, and your final speed will be 17.9 meters per second. Okay. And let's say the mass of your car is 1.30 times 10 to the third kilograms. That's 1,300 kilograms. Okay. Several thousand pounds, a couple thousand pounds. The question is, how much horsepower extra does your car have to generate to accelerate? Because you're already putting out some horsepower because you're already going, right? But what's the additional power needed to pull this off? In other words, to accelerate your car from 13.4 to 17.9 in 3 seconds, right? This needs to happen, as I said a moment ago, in 3.0 seconds to avoid the oncoming car in the other lane. You're one of these crazy daredevil driver people. So what's the additional power? Well, obviously power, let's see here. I think I'll stick with blue. Power is going to be work divided by time. So how can we find the work in a case like this? All right, this is going to be the net work. That's the total amount of work your car has to do. Okay. What we're going to do is we're going to use in order to solve for work, we know the time, we need to find the work, right? Work is the problem. Time, we're given, free of charge right there, 3.00 seconds. But work we can find by the work energy theorem, right? Because net work is delta K. Boom. Net work is delta K. So we can find delta K. That's easy enough. That's going to be the final kinetic energy minus initial kinetic energy. All right, that's what delta means. Final value minus initial value. So this is going to be 1/2 mvf squared minus 1/2. All right, the mass is constant. The mass is the same finally and initially. Your car's not adding any mass to it, right? Actually, you are draining your gas a little bit, so there is a little bit of a loss of mass, but we can ignore that. Not so important. So there you go. We have all these numbers. We have the mass given to us. Boom. We have the initial velocity given to us. Boom. We got the final velocity given to us. Boom. So we put our numbers in, and when you do this, you get for that number there 9.16 times 10 to the 4th joules. 92,000 joules approximately. 9.16 times 10 to the fourth. And then you can take that and put it up there for delta K. When you do this, you get power is going to be 9.16 times 10 to the fourth joules over 3 seconds. Divide those out and you get power is, drum roll please, where is it? Where'd it go? 3.05 times 10 to the fourth watts, so about 30,000 watts, which is equal to, if you want to put it in horsepower, which would be more standard for a car, about 40.9 horsepower. Okay, so that is the power required to pass the truck. You have to generate that many joules per second extra to accelerate your car from 13.4 to 17.9 meters per second in 3 seconds. Now this is not the total amount of power required to get the car going this speed, 13.4, right? Because eventually it started from rest somewhere down the road. This is only the power needed to accelerate the car from this speed to that speed in 3 seconds. If you had had less time to do it in, you would have had to generate more power because this denominator would be smaller. If you had more time to do it, if you could have taken 10 seconds to do it, the amount of power required would be less. Power tells you how quickly work is done, or equivalently, how quickly energy is put into a system, or how quickly energy is produced by a system. Okay, joules per second, watts. All right, that's your introduction to power right there. How quickly work is done. All right, that's it for chapter 7. See y'all in chapter 8.